Good morning. Today we'll be investigating this pulley system, and the goal is to answer the following question. Determine the acceleration of the pulley system and the tension force. The force of friction acting on the 1.95 kilogram object is 3 newtons. Assume the 1.95 kilogram object remains in contact with the surface. So in a few moments we'll come to understand how I've created this force diagram. For starters, however, that circle represents the pulley. In real life, pulleys sort of look something like that. Pulleys are used in elevators. Elevators are typically connected via a cable to a counterweight. And so let's take a look at a simulation right now to examine the motion of this system before we try to answer the question. So here is our typical pulley system. This is our pulley. Here is the weight, which will provide a force to drag the system along. And in this case, the weight is attached via a cable or string to a vehicle. Now, nothing is moving right now because my hand is physically holding the car in place. It's counteracting the force of gravity here. Here are the force vectors. Notice we have this force, the force of gravity. Because it's a string, this is the tension force. Underneath the hand, it's hard to see this, but there is also a tension force. And if we add some mechanical resistance or friction, we have a force acting in that direction. So what I can do in this simulation is adjust the mass of the pulley weight, which is what I'm about to do. And so let's press the launch button and see what happens. Notice the car moves towards the right. From this data, we can clearly see that the car is accelerating. Notice that the gap from picture to picture is steadily increasing as the car accelerates. If we reduce the mass of the car, the acceleration will be even greater. And you can see that here. So clearly these systems accelerate based on what you just saw. So let's go back to the question and see how we draw the force diagram and ultimately determine the acceleration and tension. Focusing our attention on this particular part of the system, we're going to label that force. That's the weight or the force of gravity. It's given by the formula mg. And working through the math, we end up with 49.49 newtons. Now focusing our attention on the other part of the system. In the question it says the force of friction acting on the 1.95 kilogram object is 3 newtons. So we're going to label that 3 newtons, as you can see there. So what about tension? Ultimately we have to solve for tension, but what direction is the tension in? Well, focusing our attention on that particular part of the system, it points upwards here. Now, why does it point upwards? Well, notice that gravity acts downwards, and the string is what's holding this object back. It's holding this 5.05 kilogram object from accelerating at exactly 9.8 meters per second. So because the string is holding that object back from accelerating at 9.8 meters per second, the tension acts upwards. Now focusing our attention on that object, tension acts to the right. It has to act towards the right because we know that's the only force here that can possibly move the object towards the right, as the 3 newtons is holding it back. It's acting in the other direction. Now we'll also include the weight, or the force of gravity, and the normal force, the support force, acting on that object. However, because we are assuming that this object remains in contact with the surface, these forces will be balanced, and they will be largely ignored because they do not act in the direction of motion. All right, Let's focus our attention now on the 1.95 kilogram object. Notice I've highlighted the force of tension and the friction force. Writing an F net statement, we write that F net equals tension subtract 3 newtons. In this case, friction is negative as it opposes the motion, and tension is positive because that's the only force that's going to accelerate the object towards the right. Recalling that F net is equal to ma, and substituting our mass, we're stuck. It seems that we only have one equation and two unknowns. Now let's focus our attention on the 5.05 kilogram object. For this object, we're going to label the positive direction and the negative direction, and the positive direction is downwards. Why is the positive direction downwards? That's because in physics, we normally associate the positive direction of a force with the direction of motion. This object is going to be moving downwards due to the force of gravity, and as a result, we are going to call the downwards direction positive. The negative direction will be upwards. So keeping that in mind, we write an F net statement. Notice gravity is positive and tension is negative. Another way of thinking about this, tension is negative because it's holding the object back from accelerating downwards. Gravity is positive because it's the force that's going to move the object downwards. Once again, F net is mass times acceleration, and we have another equation. It's important to note that in a string or a cable, the tension is the same everywhere. So the tension labeled for each object has to be the same because it's connected by the same cable. That's important to note. So we have two equations and two unknowns. The acceleration has to be the same for each object because they are connected by the same string. And for that reason, because it's the same string, tension also has to be the same everywhere in that string. So we're going to add these two equations together. When we add the left side of the equation, that gives us 7, and the right side of the equation gives us 46.49 newtons. And of course, by adding, we eliminate the variable of tension. Dividing by 7, we end up with this acceleration. Now the question is, does this acceleration make sense? Well, it does. It has to be less than 9.8 meters per second per second. The only way it could be 9.8 meters per second is if we cut the string. When we cut the string, the tension would be 0. But because the string is not cut, our value of 6.64 meters per second makes sense. It's less than 9.8. So what about tension? That was the second task in this question. Well, we could substitute our acceleration into that formula, or we could substitute the acceleration into that formula. It doesn't matter which formula we substitute the acceleration into. I'd like you to work on that, and after you have, you'll notice that the tension is 15.95 newtons. Now, focusing our attention on that object there, does 15.95 newtons make sense? It does. We know that the tension has to be bigger than 3 newtons, otherwise the object could not move towards the right. So for this instance, it sort of makes sense. Similarly, it makes sense for the other object. We know that the tension has to be less than 49.49 newtons. Why do we know that? Because if it was larger than 49.49 newtons, then the object would be moving upwards. But clearly from the simulation you saw, the object falls. So I hope you've enjoyed this explanation. Hope you've learned something. Have a wonderful day. Bye-bye.